people hear me? Can you people hear me?
Yes, sir.
Yes, sir.
Yes, sir. Yeah, when I'm asking you, kindly please reply, right? Okay. We shall start the session. I want everyone to concentrate little bit, okay, for the session. It's very easy, and I'll try to keep things as simple as possible. Okay, can you see the screen and hear me clearly, everyone?
Yes, sir. Yes, sir.
Yes, sir.
Okay, thank you. Because I'm sitting in a little bit low area where the signal is less, just sitting in the first floor, uh, ground floor, okay, of the entry near the Indian Bank. Okay, it's raining also over here. Okay, uh, so at any time, if you feel that the connection being loose, just let me know. Okay, students, is it fine? Okay, so we will start with today's class, and today's topic is multi-layer perceptron. Okay, multi-layer perceptron. So till now what we have seen is single layer perceptron. Now what is a single layer perceptron? Okay, so you have multiple inputs, you you multiply it with the weight, then you combine all the inputs, then you give it to an aggregation function. That is, you aggregate all the inputs, then you give it to a binary step activation function, and then if it is greater than threshold it will shoot 1, if it is less than threshold it will shoot 0. Yes. Okay, but what was the problem in that? Okay, what was the problem in that? That is, OR gate was linearly separatable, AND gate was linearly separatable, tautology was linearly separatable. Then when we had a 3-dimension input space, then that was also linearly separatable. But what about XOR? What about XOR? So AND gate was linearly separatable, NAND gate, OR gate. But what about XOR? Okay, if I draw a linearly separatable line, something like this. Okay, what about that? That is, they can only learn linearly separatable patterns. Who? Single layer perceptron. Linearly separatable patterns are the data sets which can be separated by a linear boundary. Okay, which can be separated by a linear boundary. Something like this. Can you see? You cannot classify at all. Okay, anything above this and anything below this. So this guy, Marvin, showed that in his book that it was impossible for a perceptron to learn a simply non-linearly separatable function such as XOR. So like for AND gate and OR gate when we saw, okay, for XOR you cannot do it. It cannot separate, you cannot classify. So we need to go for a little bit advanced version of a single layer perceptron. Okay. So for the plots for the XOR function, it is impossible to find the linearly separatable boundary. Something like this, if I want to draw a decision line. Okay, and apart from an XOR, there are other functions also. Not only XOR, there are few other functions which are not linearly separable. So what is indeed is the need of the R is something extension with respect to single layer perceptron. So what do we do? The obvious extension is to add more layers so that there are non-linearly computations. So what we will do is we will create a line, decision line like this and a decision line like this. Okay, sorry for this one. Okay, so a line will be like this and a line will be like this. Now we are going to draw two lines. Okay, now anything in this region we'll classify it. Okay, and anything above this and below this we will classify it as one layer. Okay, so with the help of two lines we will try to do it. Okay. So simplest use case of a classification is a linear. Can you see a linear boundary? Can you see a green color line? So anything above this line is 1 and anything below this line is 0. A decision boundary separating two different classes. This is what we saw in single layer perceptron, right? And what about with the help of three inputs? In the help of single layer perceptron, we saw the cube, right? We also saw the cube. We also saw the cube. So x1, x2, x3 hyperplane, a plane. Okay. So then anything the 0, 0, 0 was over here, and apart from that it was able to classify it as 1, and below that it was classified to classify as 0. Prediction. What is the perceptron model? What did we do, students? What is the perceptron model? What is the single layer perceptron? Very simple, right? Okay, we added up, okay, we x1, x2, w1, w2, okay, we multiply x1 into w1, x2 into w2, xn into w1, and we put it through the summation. Then we put it through the activation function. Then the activation function produce 1 or 0. Okay, this was the y predicted, 1 or 0 y predicted. So this was the formula. This is a single layer perceptron. Now what we will do is in multi-layer perceptron, we will combine like this multiple single layers plus multiple single layers. You can have g of another x w0 x0 plus w1 x1 plus w2 xn, because I want to draw true lines, right? What did I say? What did I say? How will you overcome this one? How will you overcome this one? What did I tell you? Okay, what did I tell you? Draw two lines. So one line will be for one layer, another line will be for another layer. So draw two decision layers. This is for one layer. Okay, this is how are you going to draw this boundary? X0 into W1 plus X1 into W1. Sorry, W1 X1 into W1 plus X2 into W2 plus X3 into W3. And if there is a bias, whatever it is, you can add that bias. You get this one. But if you want to draw true lines, then you will be requiring two linear decision boundaries, right? Yes or no, students? Hello, hello, students.
Yes.
You people are getting it? Whatever I'm trying to tell you, pa? Hello.
Yes.
You people are able to understand?
Yes.
Okay, very good. So now I'm going to draw another one. If I want to classify multiple things, multiple layer perceptron, I will add another decision layer, another single layer perceptron. So y equal to x g equal to x w0 x0 plus w1 x1 plus wn xn, another layer, like another layer. So I will combine multiple single layer perceptrons depending upon what type of data set I am working on. Accordingly, I can have multiple single layer perceptron. It's called as a multi-layer perceptron. It is called as multi-layer perceptrons. Okay. Okay. Where deep neural network shines. So now if you want to classify a binary class, can you see something like this is there, like this is there? Can I draw something like this, a layer, and try to segregate? Definitely no, right? I cannot do it. Okay, but if I want, if I have a class of class 1, class 2, class 3, class 4, then how many input layers I need to have? Then how many single layer perceptrons I need to have? Multiple layers of perceptrons. I need to have multiple perceptrons. For a single layer, for a two, class 1, class 2, for a class 1, class 2, okay, for a class 1, class 2, single layer perceptron, I draw like this. Okay, for an AND gate, with the help of a single formula. With the help of a single formula, with the help of this formula, I am able to segregate one class, class 1, class 2. But what about if I have multiple classes, something like this? Class 1 is there, class 2 is there. Till now, I was able to segregate only class 1, class 2. But what about class 3, class 4? If I have multiple classes, if I want to multi-class. And what about if I have this kind of a classification? This is where non-linear classification, where deep neural network shines. This is where the multi-layer perceptron comes. So what do we do? How it works? So what do? We use this particular function of a single layer perceptron, and we add, okay, embed linear layer prediction formula. You combine multiple linear layer prediction formula like this. So you can write another formula. Okay, what I am trying to say here is another genome naught of w naught x naught plus w1 x1 plus wn xn. Then you combine another g of w naught x naught plus w1 x1 plus wn xn plus another one according to your needs of how many ever classes you want to classify, which will give you multi-layer, okay, more than one single layer. This is a single layer, right? When I write the same formula again and again and try to combine it, then it is called as a multiple perceptrons. Okay, you're getting the point, students, what I'm trying to say? Hello?
Yes, sir.
You're getting the point, students, what I'm trying to say?
Yes.
Hello? Yes? Yes, students?
Yes, sir.
Yes or no? Yes or hello?
Yes, sir.
Okay. How many of you are able to understand? Quickly raise your hands in 5 seconds. Everybody, who those who are understanding, please quickly raise your hand, students. Very good, excellent. Okay, okay, students. So when I'm combining, okay, it is called as a multi-layer perceptron. Can you see? Now I have a simple one. Okay, when I want to classify something like this, a single layer perceptron. Now another single layer perceptron, the combination of two single layer perceptrons. This is a single layer, right? This is what we have been doing, AND gate, OR gate, NOT gate, whatever it is. And this is another single layer perceptron. Okay. And then when I try to adjust the weights, when I combine these two and modify the weights, then I can get this kind of a linear, non-linear classification. Another example. When I'm combining another this particular single layer perceptron and another single layer perceptron, and when I'm trying to modify the adjusting the weights of this or this, trying to adjust the weights of this and this and this, then I can get this line. Can you see? Can you see the difference between this and this? I am adjusting the weights. Nothing else I am doing. This is a single layer perceptron. This is a single layer perceptron. Okay, that is g naught w naught into x naught plus w1 into x1 plus w2 x2 x2 plus another g naught into w g of w naught into x naught plus w1 into x1 plus w2 into x2. Now I'm combining two layer perceptrons. Now on the single layer perceptron, I'm trying to adjust the weights. Okay, I'm trying to play with the weights. Then I get a decision boundary like this, which I can do a non-linear classification. The same thing over here. Now I'm trying to adjust the weight of this and trying to get this kind of a linear decision boundary. Then if you can also get this kind of a decision boundary, something like this, by adjusting the weights. So you can play around. Okay, once again. Sorry. Okay, then you can try to adjust the weights. I'm trying to adjust the weights. Okay, and then trying to play around with the single layer perceptrons. Okay, if I adjust the weights of this and this, then I can get a decision boundary like this. Okay. Now, this is what I was telling you, students. Now, listen here. Now, very careful. Okay, this is the very important concept. Okay, can you see? This is a single layer perceptron, right, students? Can I tell this is a single layer perceptron? Hello?
Yes, sir. Yes, sir.
Yes.
Yes, sir.
Okay, see, x1 into w1 plus x2 into w2. Now, what it is doing, I am this pink line, I am aggregating it. Can you see, students? I am aggregating it. Say, for example, this is 1. Okay, and also say, for example, this is 2. This is just to make you understand. So 3 into 1. Okay, let's consider 3 plus 2 into minus 1. Let's consider minus 2. Okay, so 3 minus 2 is what? We are aggregating it. So 3 minus 2 equal to 1. Okay, very important concept, students. Based on this one, very simple but very important. So 3 minus 2 is 1. So the pink line denotes the aggregation function, the pink circle, right? So it has two things embedded in it. This P1 has two things embedded in it. Okay, so this pink line is 3 minus 2, which is 1. Then this 1 is given to the aggregate activation function, binary step activation function, or a sigmoid function. In this case, okay, we will be using sigmoid function. Okay, sigmoid function is what we have been using for logistic regression. Okay, that is 1 divided by 1 plus e power minus x, e power minus x. Okay, so the activation function used here for multilinear classification, we will be most of the times we'll be using the sigmoid function, the one which we use for logistic regression. What does that sigmoid function do? It will convert the values, whatever may be the values, in between 0 to 1. Isn't it, students? Isn't it?
Yes, sir.
Hello?
Yes,
Yes.
sir.
So this particular one is put into this value, the x, and this will give you some value. Okay, this is the activation function for multi-layer perceptron. Like how for a single layer perceptron, the binary step function we used, right? The binary step function we used, right? But for here, we are using this particular one. So then the output of this activation function is given to another predictor, is given to the another value. So the same way, this is another single layer perceptron. This is another single layer perceptron. Okay, so then we are combining. Consider this is as 2 and this is as 3. So 7 ones are 7, 7 2s are 14, and whatever may be the value, 4 3s are 12. Okay, minus 12, which we are getting it as 2. Okay, then we are going to give this 2 aggregation. Okay, the pink line denotes the aggregation and the white circle denotes the activation function. So what type of activation function? 1 by 1 plus e power minus x. 1 by 1 power e power minus x. Okay, students, 1 by 1 power e power minus x. In this case, x value is 2. So now this will give you some value. Okay, now say for example, this is giving you 0 point. Say for example, because this particular activation function will squash, will squeeze in between 0 to 1, right? So for example, this value is 0.3, it is giving, this is just to make you understand, and this value is giving 0.5, this is just to make you understand. Okay, 0.5, this is make you to understand. So 0.3 is the output of P1 and 0.5 is the output of the P2, which is the output of the activation function. Now this particular 0.3 into, okay, the output of P1 is 0.3 into, say for example, if this is W1, W2, W3, W4, this is going to be W5 and W6. So W5 into output of P1, which is 5 into 0.3, okay, plus okay, 0.5 into 0.2. This is 2, 0.5 into 2. Then you aggregate it. Now, say for example, you get whatever maybe the value 7, say for example, then 7 is put again into this activation function. 7 is put into the activation function, and then you can say for example 0.8 you are getting. 0.8 you are getting. This will be the predicted value. This will be the predicted value. Okay, students. So this is how the entire multi-layer perceptron works. This is how the entire multi-layer perceptron works. Okay. Now, if there's a one layer, this is I am showing you this is a particular one layer. Now I will tell you what it is. This is the input layer, students. This is called as an input layer. This is an output layer. Okay, in multi-layer perceptron, there are 3 layers. This is the first one is the input layer. Can you see x1, x2, x1, x2? This is a layer. The y predicted is the output layer, and P1 and P2 are called as the hidden layers. Are called as the hidden layers, which we don't know. So which will go through the pattern. So here we don't know what is the input itself to the hidden layers. We don't know what is the output. We don't know what is the output. Okay, so the hidden layers. So we are going to calculate it, which is dependent on the previous layer. That is, this particular hidden layer is dependent on the previous layer input layer, and output layer is dependent on the hidden layer. Okay, so we have 3 layers: input layer, hidden layer, and the output layer. In this case, we have only 2 hidden layers. Okay, one layer 1. Okay, one layer. This is the layer 2. I will show you. Okay, might be you will be able to understand in the next slide in a better way. Okay, this is layer 1, layer 2, layer 3. In layer 1, we have 2 neurons which are hidden. Okay, 2 neurons which are hidden. Okay, now consider a slightly complex graph like this. A complex graph. Okay, see how many inputs are there? 1, 2, 3, 4. Okay, layer 1, layer 2, layer 3, layer 4. Layers. This is the second hidden layer. This is the third hidden layer, and this is the output layer. This is the output layer. Okay, there can be a particular structure like this also. Now, if you see this one individually, if you see, can you see this is a single neuron? Can you see this is a single neuron? We can say, right? Okay, can we say this is a single neuron? Can we say this is a single neuron? So what the point I'm trying to say is multiple single neurons work together, okay, to form the multi-layer perceptron. That is the point what I am trying to say. Where, okay, can you see where these two functions are embedded in one, students? Where these two functions are embedded in one. Okay, where these two functions, this and this, is embedded into this one. So this is not there. Just imagine this is not there and this is not there. These two things are combined together, which we are representing as this one. So the first, the outer layer is the summation layer and the inner layer is the activation layer. The outer layer is the summation layer and the inner layer is the activation layer, where both the things are happening in one go. Both the things are happening in one go. That is what I'm trying to say. Okay. Okay. So here multiple hidden layers. Okay. Can you see multiple hidden? So this is the input layer. This is the hidden layer 1. This is the hidden layer 2. This is the hidden layer 3. And this is the output layer. Okay. You're able to understand? Hello? Are you people able to understand?
Yes, sir.
Yes, students? Okay. So let me proceed further. Now, what is multi-layer? This is the basic concept, what I have told you. What was the problem in the single layer perceptron and how multiple layer perceptron works. And let's see a more brief in-depth detail of multi-layer perceptron. So as I told you, okay, there are input layer. Okay, students, this is a hidden layer and this is the output layer. So layer 1 output is given to as the input to the hidden layer. Okay, now there in this layer it will do two functions, which is the summation of this and activation of this, and this output is given as an input to this layer. Very simple, right? In basic, by looking at the diagram itself, it's a very basic common sense. So layer 1 output is given as an input to the layer 2. Layer 2 will perform some computation based on the layer 1. Okay, and then the layer 1, layer 2 output will be given as an input to the output layer. That is the output layer. Can you see? It's the output layer. So each perceptron sends a single multiple signals. Each perceptron sends multiple signals. One signal going to each perceptron in the next layer. Can you see? If you consider this line alone and this line and this one, can we call this as a single layer perceptron? Isn't it, students? Hello? Hello?
Yes.
Yes. Okay. Now, if you consider these two, can we call this as a single layer perceptron? Yes. Isn't it,
Yes.
students?
Yes, sir.
Yes. Now, if you can call this, this is also a single layer perceptron. So the point what I'm trying to say is, okay, all the connections are there. Okay, all the inputs, that is each neuron is sending to each, so that they are forming a network of multiple single layer perceptrons. Now you can also say this is also single layer perceptron, where the input is dependent on the calculation of the input is dependent on the previous layer, the hidden layers. So the output is dependent on the hidden layers. There can be multiple layers such that MLP can become a complex system. Okay, complex system. Okay, MLP, otherwise called as a neural network. Now, what is a neural network? Okay, multi-layer perceptron is otherwise called as a neural network. A 3 layers. Can you see 3-layer perceptron? Layer 1, layer 2, layer 3. Perceptron is otherwise called as a non-deep or shallow neural network. It is called as a non-deep or a shallow neural network. But with MLP with more than 4 layers. Can you see? With more than 4 layers. Okay. layer 1, layer 2, layer 3, layer 4, and layer 5, you can call it. More than 4 neural is called as a deep neural networks. It's called as deep neural networks, where the system becomes more complex. Then you can just imagine, like in our human brains, there are billions and billions of neurons, and each neuron is connected to the other neuron. Then how our complex system, our creator has created, see or no? Okay, so this entire concept of brains of the neurons, okay, have called as the entire connecting of one neuron to another, another neuron to another neuron to another, and every neuron which is connected to every neuron is connected to every other neuron in a network is called as a fully connected network. This particular architecture with 3 input layers and 2 hidden layers, layer 1, layer 2, and one output layer, with each hidden layer has 4 perceptrons. Can you see every layer is connected to every other layer? This is connected to 1 2 3 4, 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 this is connected to everything. Is called as fully connected MLP, where every neuron is connected to every other neuron in a network. Something like in networks, which concept have you studied? In the networks, which concept have you studied like that? You people have studied networks, right? Yes or no?
Yes, sir. Yes, sir.
Wow, what type of network can you imagine with respect to this one? Just to understand, I'm not comparing,
The
Yes,
star
students.
topology.
You can have star topology. Okay. See how mesh works. Okay. So something like this, right? Where every particular node is connected to every other node. Yes.
Yes, sir.
Okay. So this is all about thing. So now, what are the different types of activation function we have studied? Okay, so binary step activation function, but here we will be using logistic function. Activation, right? The activation happens with respect to a sigmoid function. This is a sigmoid function. This is what we have studied, which will convert the value, a beautiful curve we saw, right? Which will convert the value in between 0 and 1. Okay, which will convert the value between 0 and 1. Okay, now students, feed forward neural network. But this is what we have been studying. Okay, in single layer perceptron also, feed forward neural networks. So now what will happen is, student, I have just told you, this is the simple example of feed forward neural network, student. I've just told you, right? This is a feed forward neural network. So we are combining these two, giving it to the input. Okay, then we are aggregating it. Then we are putting it into the activation function. Okay, then the activation function output will be given as an input. Then we are multiplying with the weight, and then we are giving it. This is all about feed forward, students. This is all about feed forward. Okay. And the same logic what we have studied in single layer perceptron, that is also feed forward one. A single layer perceptron, there are no hidden layers, so the number of layers is 2 in the single neural network. Okay, a single neural network. Okay, so this is a layer 1, and the output will be the layer 2. There is no hidden, right? Okay, so directly we can give the summation and give it to the activation function, directly get the output. So there are only in the single layer perceptron, there are only 2 layers. One is the input layer, the next one is the output layer. Okay, MLP on the other hand, at least one hidden layer. Okay, which is composed of multi-layer perceptron, at least one hidden layer. An example of feed forward with one hidden layer is shown. Okay, so artificial neural network, I have told you, right? Here I have also said, right? What is an artificial neural network? Deep neural network, ANN. I have, okay, it's called as an ANN, otherwise called as an ANN also. Okay, in ANN, okay, in ANN, in which the connections between the node does not form a cycle. Okay, in ANN, the connection between the nodes does not form a cycle. Okay, but in the opposite of the feed-forward neural network, the paths are cycled. The information in feed-forward, okay, very important point. The information is only passed from one layer to another layer and from another layer to another layer. That is the input and the weightage. You multiply it, you aggregate it, you do take the activation function, the output of the activation function, you multiply with this weightage and you give it. Okay, and then here again you aggregate it and again you take the particular activation function. That is, the information is passed only in the forward direction. I will teach you with help of a problem also. Okay, here ANN is the connection between the nodes does not form a cycle. Okay, make sure ANN. So while the data is passing through the multiple hidden layers, it always moves in the forward direction. As I told you, okay, this is the example I have told you, right? The data moves only in the forward direction, from this to this, from this to this. Then you take the aggregation and activation, then you multiply with this, you take the aggregation of these two, and then you activation, and then you forward it. That's all. Okay, the data is passed only in the travels in the forward direction in the network, first through the input nodes, then through the hidden nodes, and finally through the output nodes, and finally through the output nodes. Okay, then the feed forward neural network are primarily used for supervised learning. So now students, now very important, now see here, when you have a particular, okay, input layer, you have an hidden layer, one hidden layer, layer 1, layer 2, layer 3. Okay, now layer 1, what happens is you pass it over here, you pass the input to this. Okay, that is say for example 1, 2, the weightage is say for example 0.1, then this weightage is 0.2, this weightage is 0.3, this weightage is 0.4, 0.5, 0.6, 0.7. Then we have say for example again 0.1, 0.2, 0.3, whatever it is. So what I do, so 1 into 0.1 plus 2 into 0.2, whatever the summation you are getting. Okay, then it will be put into the sigmoid activation function. Don't worry, I will explain you with the help of a problem. Okay, then the activation function will give that input is added up with this weight, then this activation function is added up with this weight, this activation function is added up with this weight, and then again what you do is you aggregate all these weights, you aggregate all these weights, you aggregate all these weights. Okay, then whatever may be the weights, again you put into the activation function. That is, every layer from here on will have two things, right? Will have two things. One is the aggregation and one is the activation. Activation is the sigmoid in this case. So one is the aggregation, one is the activation. So one is the aggregation, one is the activation. One is the aggregation, one is the activation. Okay, so you aggregate it, from the aggregated value you take the activation the same way over here also. You take the activation. So then the activation function will give you some classified output. Okay, which will be between 0 and 1. This type of classification, where one hidden layer is called as, where only one output is there, is called as a binary classification problem. We have a single output neuron and use a sigmoid activation function. But you see this one, a fully connected network where every layer is connected to every other layer. Okay, connected to this, connected to this, connected to this, connected to this, such a complex graph. Okay, and it goes, and see her. And see here, there are multiple outputs which is coming. Then this type of network you can go for multi-class classification, So this type of network you can use it over here. And this type of network and this type of network, which is either 0 or 1, whatever it is, you can use it to this one, binary class classification on a non-linear data. Okay, on a non-linear data. students, you're able to understand whatever I have told you? How many of you have understood till here? Raise your hands. Till here, raise your hands. I really hope that you people have understood. Okay, so you people, with this I will stop. Okay, with this I will stop, because if I start now, it will take another 40 minutes, okay, to complete. So I don't want to. Okay? Keeping this in mind, we will proceed forward. Okay, keeping this in mind, we will proceed forward to the next class. Is that clear, students? Okay, now you people tell me how much have you understood. Put it in the chat box, and then you people can leave.